Mathematics for Computer Scientists, Chapter 2. In Chapter 1 we saw that numbers have got three parts to them. There's a sign, there's a magnitude, and there's an exponent. In exactly the same way, algebraic terms have three parts to them. There's a coefficient, a variable, and an exponent. If the coefficient or the exponent is 1, we generally don't bother writing it, but don't forget it's still there. If we add a number of terms together, we call that a polynomial. And a polynomial is normally written with decreasing powers of the main variable. In the example in the book, it's ax to the fourth plus bx cubed plus cx and so on. You can add terms together as long as the variable and the exponent are the same. So you can add 2x to 3x to get 5x, that's fine. If you add 4x cubed to 5x squared, you get 4x cubed plus 5x squared. You can't simplify the expression any further. If you subtract 4y squared from 5y cubed, you get 5y cubed minus 4y squared. Again, you can't simplify that any further. When you multiply terms together, you multiply the coefficients together. If the variables are the same, you add the exponents, and if the variables are different, you can't do anything more. So 3x times 4x cubed gives us 12x to the fourth. 3x means 3x to the 1, and 4x cubed is obviously 4x cubed, so the 1 and the 3 add together to make 4. And if you multiply 4y cubed by 2x squared, you get 8x squared y cubed. Now I'd like to look at sketching curves. Starting with a straight line, you need 2 points to draw a straight line. The easiest 2 points to find are when x equals 0 and when y equals 0. So if we had the equation y equals 2x plus 4, you'd set x equal to 0, in which case y would equal 4, which would give us this point here. And you can set y equal to 0, in which case 2x plus 4 equals 0, so 2x equals minus 4, so x equals minus 2, which is this point here. And when you've got the 2 points, you can draw the straight line between them. If we have a quadratic curve or a higher order curve, the quickest way to do it on paper is to draw yourself a table. Choose the simplest value of x, which is obviously 0, and put the value into the equation. So in this equation, 2x squared minus 3x minus 2, if x is 0, that term goes out, that term goes out, so y is equal to minus 2. I've put it in the middle of the table here so that I've got space to explore the curve on either side of 0. So let's take the next easiest number, which is 1. That would be 2 minus 3 is minus 1, minus 2 gives us y is equal to minus 3. So let's now look at 2, because I'm just moving along the x values here. So if we put 2 in, 2 squared is 4, times 2 is 8, 8 minus 6 is 2, 2 minus 2 is 0. As we travel from 0 to 1, the curve is going downwards, but as we go from 1 to 2, the curve has gone back upwards. So we've got that sort of shape. Also, at this point here, we found one of the roots, which means we now really know the shape of the curve. The centre point is around there, so we can just fill in the other numbers, and there's our curve. You can do this for any curve, even curves with discontinuities. Now we get on to the intersection of curves. Let's start with straight lines. Take the line y equals 4x minus 3. It's true to say that y is equal to 4x minus 3 at any point on that line from x equals minus infinity to x equals plus infinity. It's also true to say that y equals minus 2x plus 7 anywhere on that line from x equals minus infinity to x equals plus infinity. And there's one point in the whole universe where both statements are true at the same point, and that's where they cross. Now, because we've got y equals there and y equals there, I can simply set the two equations equal to each other, and then with a little bit of algebra we can find that x equals 5 over 3 at the point of intersection. If we substitute that value of x into one of the curves, this one for example, we can find with a little bit of algebra that the point of intersection is y equals 11 over 3. Did we get it right? Well, the quickest way to check is to put that value of x into the other equation and see that that's the same. 11 over 3, 11 over 3, so they are the same. I call that the sanity check. Now let's look at the intersection of higher order curves. We'll look at the intersection between a quadratic and a straight line. As before, we've got y equals and y equals. We can set these two equal to each other, which is there. A little bit of manipulation and we get a quadratic. This is the quadratic of the points of intersection, remember. Looking at this quadratic, there are no obvious roots, so we'll use the formula. In this case, a is minus 1, b is minus 1, and c is 12, so we put those numbers in. We get that x is equal to 3 or minus 4. If we substitute those into the linear equation, when x equals 3, y is equal to 11, and when x equals 4, y is equal to minus 4. As in the previous example, we must check these values, so we'll put those x values into the quadratic equation. So I'll make a bit of space. We put it into the quadratic equation, so when x is equal to minus 3, y is equal to minus 11, which agrees with the previous one, and when x equals minus 4, y is equal to minus 4, which also agrees with the previous one. So the chances are we've got that right, so let's have a big tick for that. The next step is to review matrix algebra. If we have two matrices A and B, addition is carried out by adding corresponding terms. So it's A11 plus B11, A12 plus B12, and so on. Subtraction is similar to that, in that you subtract A minus B, it's A11 minus B11, and so on, so the matrix becomes that. Multiplication is a little bit harder. If we're multiplying A by B, I think in terms of taking that column from the B matrix and putting it across the top of the A matrix. So we'll start with B11, B21, and then we have A11 times B11, that's there, plus A12 times B21, which is there. And then on the second term we've got A21 times B11 plus A22 times B21, which is there. Then we take the second column, lay that across the top here, so we've got B12 and B22. That's meant to be a 2. And so now we multiply A11 by B12 plus A12 times B22, and so on. I want to use these three operations now to look at geometric transformations. Assuming we have an array of points, which is a shape somewhat like this, that's 2, 2, 4, 2, 4, 4, 3, 5, 2, 4. Translation is carried out by adding the translation matrix to the array of points. So there's our original array, there's the translation, which is dx of 5 and dy of 7. 2 plus 5 gives us 7, 4 plus 5 gives us 9, 2 minus 7 gives us minus 5, and so on. And the result looks like this. So the point, the corner here, which is 2, 2, has now moved. 2 has gone to 7, and that 2 has gone to minus 5. So that 2 has gone to 7, and that 2 has gone to minus 5. So the point translates to there, and each other point transfers in the same way. That's the translation matrix. Now we look at the scaling matrix. That's the scaling matrix, and this time we're going to multiply our array by the scaling matrix. So for example, if we scale by 2 in the x direction and 3 in the y direction, there's our original matrix, there's the scaling matrix, and as before we take that column and lay it across the top here. the y value is 0, so all these terms will disappear, so we end up with just 2 times this column here. So 2 becomes 4, 4 becomes 8, and so on. Then we take the second column and lay that across the top. Now this time the x value is 0 and the y value is 3, so we're going to get 3 times each one of these, so 2 becomes 6, 4 becomes 12, and so on. The result of that is a scaling which is 2 in the x direction and 3 in the y direction. So our little house has become a skyscraper. And then finally we look at rotation. We're going to rotate a point here to a point here, so that's any point in the Cartesian space, and we're going to rotate by an angle of theta. And there's the rotation matrix, and that's our original point rotated to give us our final point. So as before, we take the matrices, we take the first column, we'll lay it across the top, and then we're going to get 2 cos theta minus 2 sin theta, which gives us the 0, and we just carry on multiplying all the way through. Then we take the second column, lay that across the top, 2 sin theta plus 2 cos theta, which is that term there, 4 sin theta plus 2 cos theta, which is that term there, and so on. And the result is a rotation of that. Notice that's 45 degrees, so this is horizontal, and now it's become an angle of 45 degrees. And that's the end of Chapter 2.